Inside a turbulent storm cloud, millions of ice and water particles violently collide, building an immense electrical charge until it finally tears through the sky. At its peak, that single strike heats the air around it to roughly 50,000 degrees Fahrenheit. That is 5 times hotter than the visible surface of the sun. To be precise, that comparison measures lightning specifically against the sun's photosphere. That is the outer layer of the star we actually see emitting light, and it hovers around 10,000 degrees. The sun's core, by contrast, churns at a staggering 27 million degrees Fahrenheit. And as you move outward from that visible surface into the sun's atmosphere, the corona, temperatures spike back up into the millions of degrees. The sun as a whole produces infinitely more power than a thunderstorm, but if we were to take a measurement during that specific blinding flash, a bolt of lightning genuinely outburns the star's visible surface. The physics at play here rely on a strict distinction between temperature and total energy. Temperature measures how highly energized individual particles are, while total energy measures the collective heat present across an entire system. This diagram compares how that dynamic scales. The sun holds its lower surface temperature across a sphere spanning 1 million kilometers, fueled by continuous nuclear fusion for billions of years. Now look at this bright spike. A lightning channel hits its 50,000 degree peak in a thread of air centimeters across, and holds that extreme state for just millions of a second. Lightning wins on peak temperature, but it loses on total energy. It is a hyper-concentrated micro-event, vastly different from the continuous, massive volume of a burning star. Before a strike even happens, strong updrafts inside a thunderstorm push tiny ice crystals and water droplets into constant collision. This friction separates the electrical charges, sending positive charges to the top of the cloud and pooling negative charges at the bottom, building up billions of volts of tension. The air separating that cloud from the ground is a natural insulator. It possesses extreme electrical resistance, meaning it actively fights the flow of electrical current. This schematic maps how the stored charge finally breaks through. Faint, invisible channels of ionized air called stepped leaders snake downward in short bursts, hunting for the path of least resistance through that insulating air. As those leaders get close, positive charges on the ground surge upward from trees and buildings, trying to connect. The moment a downward leader and an upward streamer meet, the circuit closes. Without the atmosphere's extreme electrical resistance blocking the path, that charge would disperse quietly. Instead, fighting that massive resistance creates the exact physical friction required to generate Earth's hottest phenomenon. What you actually see during a thunderstorm is a massive surge of current that blasts back up from the ground into the cloud. This is the return stroke. It drives tens of thousands of amperes through a channel roughly 1 inch wide, traveling at nearly 1/3 the speed of light. Because the air fiercely resists this immense current, the electrical energy converts instantly into heat. The air gets so highly energized that electrons are ripped entirely away from their atoms, transforming the gas into a 50,000 degree soup of charged particles, known as plasma. That intense heat forces the surrounding air to explode explosively at supersonic speeds. This rapid expansion creates a massive shockwave that rolls through the atmosphere and eventually decays into the sound we recognize as thunder. If that strike happens to hit a sandy beach, the physical evidence is left behind in the dirt. The immense heat instantly melts the silica in the sand, cooling into hollow, glass-like tubes called fulgurites. The deafening crack of thunder echoing across a valley, and these delicate glass sculptures buried in the ground, are both the direct result of a 1-inch thread of air briefly becoming plasma. This brings up a logical question. If lightning is 5 times hotter than a star, how do roughly 90% of humans struck by it survive without being completely vaporized? This diagram illustrates the mechanics. While the heat is incredibly intense, it is restricted to a 1-inch wide plasma channel, severely limiting its footprint. Because the event is over in fractions of a second, thermal energy cannot transfer deeply into tissue. When humans are severely injured or killed by lightning, it is rarely due to thermal burning. The damage is caused by the massive electrical current passing through the body, which can severely disrupt the heart's rhythm and the nervous system. We see this survival principle applied at a massive scale in structural engineering. Lightning strikes the Empire State Building dozens of times every year, but the steel structure effortlessly absorbs and redirects the brief temperature spike without melting. Lightning is a violent, momentary rebellion of physics. For a fraction of a second, are defined entirely by their brevity.